Okay, let's dive into a hidden universe you interact with every single day but probably never actually see. It's this world of microscopic patterns and, honestly, monumental challenges, where the simple act of making an impression is one of the most complex things in modern manufacturing.
So let me ask you this. What does a super efficient solar panel have in common with, say, an ancient wax seal? I know, it sounds like the start of a bad joke, but the answer connects the distant past to the absolute cutting edge of the future. And that answer is a process called embossing.
So here's what we're going to cover. First, we'll see why this is so much more than just a simple stamp. Then we'll dig into why the material itself is like half the battle. We'll walk through the high-pressure process where pretty much everything can go wrong, try to understand why predicting all this is so darn difficult, and then, finally, we'll see the incredible future this tiny process is set to unlock. Right, let's start with the basics. We've all seen embossing, right? Think of the raised letters on a fancy book cover. But we're about to shrink that whole idea down, way down. At its heart, embossing is pretty straightforward. You've got a mold with a pattern, you've got some material, and you just press them together. You know, like a notary stamp or pushing a signet ring into hot wax. It's simple, it's effective, and it's been around for thousands of years. But what happens when the pattern you're trying to press is smaller than the width of a human hair? Well, all of a sudden, that simple act of pressing turns into this incredibly complex dance of physics, chemistry, and high-stakes engineering. And this quote, it just nails the core problem. At the micro level, dozens of different variables. We're talking everything from temperature and pressure to the exact chemical makeup of the material can completely ruin the final product. Getting it right isn't just an art form, it's a massive scientific headache. All right, so the first big hurdle you got to get over? It's the material itself. You can't just emboss anything you want. The stuff you're working with has to be absolutely perfect for the job. And what's so wild is the huge gap between what engineers want and what they actually have. I mean, ideally you want materials that are super strong, really stable, and hard. But in reality, the common polymers they use each have a kind of fatal flaw. PDMS, it's just too soft. PLA has this high crystallinity, which means it solidifies in weird ways that can warp the delicate details. And PCl, it just gets weaker and less stable over time. It's just this constant, frustrating series of trade-offs. And the problems just keep piling on top of each other. The polymers don't conduct heat well, which creates hot and cold spots that can totally ruin the pattern. And it's not just the polymer. The molds themselves are a headache. Ceramic molds can literally burn up at high temperatures, while metal ones have to be unbelievably strong to not deform. And to top it all off, the mold and the material expand at different rates when you heat them up, which can basically wreck the entire process before it even really gets going. Okay, so let's say you've picked your less than perfect material. Now you have to actually do the embossing. And it's a process where every single step is just loaded with potential for failure. You know, in a perfect world, it's a pretty simple four-step cycle. You heat the polymer up so it gets soft and pliable. You press the mold into it to make the pattern, you cool everything down to lock that new shape in place, and then you pop it out of the mold. Looks easy on paper, right? Well, of course, in the real world, it's almost never perfect. Every single one of those four steps is a minefield. So what does that failure actually look like? You get this whole cascade of different defects, like unfilled areas. That's a failure in step 2, the pressing stage. It's when the polymer just doesn't flow into every tiny little nook and cranny. Loss of detail is kind of like a weak, blurry wax seal. But then you get something like springback. Oh, this has to be so frustrating for engineers. You do everything right, and then when you take it out, the material just elastically snaps back a little, erasing all your hard work. Or maybe worst of all, fractures, where in that very last step, demolding, the whole thing just cracks and falls apart. So your first thought is probably, well, hey, can't we just use a supercomputer to figure all this out beforehand? And yeah, that's the dream. But predicting imperfection at this scale, it is a massive challenge all on its own. And here's the thing. Running endless trial and error experiments in a lab is incredibly expensive and slow. But creating a computer simulation that can actually model all these variables with any accuracy is also incredibly difficult. It takes a ridiculous amount of computing power and time. This chart really puts it into perspective, doesn't it? Simulating a normal industrial process might take a few hours, maybe a couple of days on a computer. But to accurately simulate just one micro embossing run, oh, you're talking weeks, maybe even months of computer time. The complexity is just on another planet.
And the fundamental reason it's so difficult is that there's just no off-the-shelf software you can buy for this. The physics of what's happening are so unique and so complex that standard simulation tools, they just can't handle it. Researchers often have to build their own custom, incredibly complex models completely from scratch.
So what do you do with all this chaos? Well, researchers try to catalog it to bring some order to it all. This table does a great job of grouping all those defects we saw by what actually went wrong. Was it the shape not holding, the mold not filling, the whole structure just breaking, or the surface itself being ruined? It's basically a roadmap of everything that can and often does go wrong.
Okay, so after hearing about all these problems, you might be thinking, why bother? Seriously, why go through all this trouble for a tiny little pattern? Well, it's because solving these microscopic problems is the absolute key to unlocking a truly gigantic future.
And here it is. Here is the aha moment. The reality is more than 90% of these seemingly niche challenges are the main roadblocks preventing us from mass-producing the next wave of technology. Mastering this process isn't just a small improvement. For a lot of things, it's the only way forward.
Let's take batteries. We all want our batteries to last a long time, right? That's energy density. And we want them to charge up super fast. That's power density. Usually, you have to pick one or the other. But micro-embossing could let us structure the inside of a battery in a way that gives us both, and that would be an absolute game changer for everything from our phones to electric cars.
Or think about solar energy. By creating these huge arrays of microscopic lenses on the surface of a solar cell, you can dramatically increase how much sunlight it captures. The problem isn't designing it, it's manufacturing millions of them, perfectly and cheaply. That is an embossing problem, and solving it is how we make solar power way more effective.
And the impact gets incredibly personal, too. This same technology is critical for creating those lab-on-a-chip devices that give you rapid medical results. It's also used to create the surfaces of advanced medical implants that our bodies are less likely to reject. So getting this tiny process right has huge implications for our health. You know, we started with a simple wax seal, and somehow we ended up talking about the future of energy, medicine, and computing. It really just goes to show you that sometimes the biggest revolutions are built on the smallest of foundations. So with so much riding on this tiny process, what do you think will imprint next?